Oh, Kathleen's back. Hopefully she's feeling better. Aiden's back. Oh, yeah, he might have been here last week. Probably. I'm just not that smart. Hopefully you can all. Oh, look at that. Hi, Lauren. Oh no, go
Did
ahead.
you ever did you ever find out when school ends?
No, I have not. Unless. Oh, oh, I got an email from Mr. Casey's brother, of all people. Um, oh, let's see. Zoe Watson just sent somebody an email. I don't know what it says. The last day of online learning for K to 12 is Friday, June 12th. The last day, and all learning options and courses for credit will be completed. Work is supposed to be completed by June 12th. And it says we're,
So far away.
yeah. Oh, 9. We'll see how some of this goes. Apparently, they want us to start going back to school on June 1st. And I'm just reading this like right now. Uh, because some people have childcare that they haven't been able to get and whatnot. So I don't particularly want to have to drive to Sussex for to sit in a room that it's not like I can do anything different than I can't do here. But I think they probably just want to keep tabs on us is basically why they want to do that. But I don't know. Holy smokes, we got all sorts of people here.
Just you or the students too?
No, no, you guys aren't gonna change. It's just for staff. So, but it's yeah. I what I do here is what I would do there, and it's like okay, sure. And then what do you want me to do? I'm gonna sit around, and they probably are. Well, Lord only knows. Thinking that teachers aren't doing as much as they should. Some people probably want us to be doing more. I have no idea what the rationale is why they would change everything, but we'll see. Um, but yeah, you guys, according to that, what did I say, the 12th? So we've got some stuff to go through. Uh, Friday, I went over, for those of you who weren't here, we kind of finished going through and I wrote answers to all of this. We talked about a lot of the stuff at the beginning is converting a base to an exponent gives a number. A log with a base of a number gives an exponent, and it's going back and forth. Um, then we did some evaluations. I didn't do the graph of those because it's just -1 is a tenth. One, one, two, three, 4, 5, 6, 7, 8, 9. So it's somewhere up here. E is a little bit different and we're going to talk about that today. The inverse of this is log base 10 of x. The inverse of this is, I always get that mixed up, ln x. Rewrite as in the alternate form. Evaluate. This was the kind of challenge to estimate the numbers in. I legit estimated them and guesstimated, and then I actually figured them out on the calculator. So the log base 2 of 100 is 6.64. I said, that's 6.5. The log base 5 of 546 is 3.92. I said 3.8. We'll show you eventually a way to do that with a calculator. So I have 2 weeks before they expect us to go back to work. We'll see how that goes. So those are all up there. Today we're going to talk about E. On your calculator, you have the button log, which we said was log base 10. There's also a button that's ln, which is log base E. And they have different functions. Paired with this is the button 10 to the x. On my calculator, I have log and 10 to the x. Those are inverses. 10 log gives me 1. 10 to the 1 gives me 10, and this kind of can unwrap things. The partner for ln is e to the x, which on my calculator, if I do this, I have ln and e to the x. And that's got all sorts of different things. E is a number. What we need to worry about is like it's 2.718281, yada, yada, yada. It's irrational. It goes on and on forever. But what is it? It's called Euler's number, and it's for this mathematician from the 1700s named Leonhard Euler. And it's not Euler, it's Euler. I learned that eventually. Um, and it comes from a number of things. But it's this crazy long irrational number. We know it to trillions of decimal places because it's evaluated a couple of different ways. This limit is a calculus bit. It says, here's our expression, 1 plus 1 over n to the power of n. As n gets bigger and bigger and bigger and bigger and bigger, when it gets to or approaches infinity, it's going to get to that number. That doesn't make a whole lot of sense right now. If you take calculus in 12b, it will. But if I extend this graph all the way over out my basement wall, 1, 2, 3, 4, 5, as it gets bigger and bigger, this blue line is going to approach, but it's kind of asymptotic. It's not actually going to get there because we can't really get to infinity. This symbol is I just have to restart writing the word. Summation. This means add up. 1 over k factorial, and we'll talk about what factorial means in a second, from when k is 0 all the way up till infinity. So 1 over 4, 1 over 0 factorial, 1 factorial, 2 factorial, 3 factorial. Well, that's 1. That's 1. That's a half. This is a sixth, a 24th, and that's going to keep going, and you're adding little itty bitty bitty bits. And this is another thing that, I mean, it's hard to comprehend, but you can actually evaluate that. And you get this number, E. And a factorial, like, why is this 24? And this is part of pre-calc 12b. 4 factorial is 4, whatever you start with, times every natural number below it. So 4 times 3 is 6, times 2, 4 factorial. 4 times 3 is 12, dummy. Times 2 is, times 1 is 24. 5 factorial is 5 times 4 times 3 times 2 times 1. 20 times 3 is 60, so that's 120. So it grows. It's not actually an exponential thing. It's a crazy geometric sort of thing. But that's where this number comes from. It is fundamental to a whole bunch of math. This is something, if you were American, Andrew Jackson was the 7th president of the United States. He had 2 terms. He was elected in 1821, 1828, 1828, 2.718281, 828, and then we have this 459045 because it's a triangle. If you need to know 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, if you needed to know 15 decimal places of E, well, there's kind of an idea how to do this. Somebody at Harvey Mudd College figured this kind of anecdote out. So mathematical consonant, Swiss mathematician E. It's um, one of the kind of, when I was in high school, the 5 fundamental constants: 0, 1, pi, I, and E. There's actually a relationship. That's just more. You can relate e to the power of pi times I plus 1 equals 0. That's Euler's identity. Well, this statement mathematically holds true. 1, 2, 3, 4, 5. It has the 5 most important numbers in mathematics, all wrapped up coincidentally in one formula. Um, that's just something that's nifty. You have to do imaginary numbers and a different set of coordinates to talk about that. That's just a whole bunch of fun information that I looked at and is really not all that important. Um, this is the graph of, well, we know we can do the graph of y equals e to the x. If we do our initial kind of table, -1, 0, 1, well, this is 1 always, 2.71828, da 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 da. Well, over 1 up, that point is 2.718. If I had have done that correctly, now what are the odds I can fix this? No, shoot. 1 and 2.71, da 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 da. -1, well, I can go to my calculator. 1 negative raise e to that power, 0.37, which would be somewhere about there. The inverse of that, x equals e to the y, which goes to y equals log base e of x, or ln x. We have that same table where the inverse, 0.37 and 1. 1 and, sorry, -1. So 0.37 and -1. 1 and 0. 2.718 and 1 and 1, 2. So we have those 3 points. So it's generated the same way. It's a little bit trickier to do neat, pretty graphs with because those are all decimals. So when we graph log functions like we did with exponential functions, just a sec. Uh, like, did you see the email? Did you see the email? He's sending messages to multiple places. But we'll see what happens. I'm not driving. Well, we'll see what they want us to do. We're not going to do a whole lot of graphs with these because they're messy. They're harder to do. This is something you would use on a graphing calculator. You know, Mr. Casey's brother says schools must be reopening to kids too. And it's like, but the email says everything isn't. So this is going to be, stop reading messages. Oh, no, just Khan Academy. So evaluating. This is something you have to have a calculator for. So you're going to need a calculator. As long as you had a scientific calculator that had sine, cos, and tan, um, you're going to be able to do this. Well, anything to the power of 0 is 1. E to the power of 1 is 2.71828. 1, da 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 da, who cares? E to the power of 3. We can do all of this stuff. It's got to be done with a calculator. Uh, -1 E. I just did this. 3, 6, 8. -5. Whoops. This is 0.0067379. Ln of, oh, that one, do we need to use a calculator? Ln of 1 should be 0. Ln of 3 is e to the 1.0, not 10. That's horrific. 1.0986. 5 ln. All of these keep going, so they're approximations. 20 ln. Ln of e. Well, if we did log base 10 of 10 equals something, 10 to the x equals 10, so x was 1. Log base e of e, well, e to the x equals e, x must equal 1, so the natural logarithm of the number e is 1. Same idea, log base 2 of 2 is 1, so on and so forth, and all of that. So, calculator stuff, leave me alone. Evaluate with some log properties. So, these are the same kind of things that we've done. E to this equals something. If I convert this, e to a power equals e to the 5th. So this must equal 5. Ln of e, this bit here is 1. So this is 4 times 1, which is 4. And I'm going to do all of these ones first. Ln of e to the -7, if ln of e to the 5th is 5, this one should be -7. When we have a radical, this is going to be the same as ln of e to the half, which is, well, ln of e is 1 by the same logic. That's a half. These are products. Well, the natural log of 1 is 0. And we can double check some of these. 2 times 1 ln equals ln of e squared. So this business, the 3 stays out front. We know that is 2. That is 6. Now we've got these logs in as an exponent. The answer to this sort of thing, if I tell you that is 15, that one is 5. Because, oh, see, this is one of these things. It's like, well, that's the answer. Now let's go and logically think of why that is. 2, 2. How do we? Oh, yeah. Stupid. write this in logarithmic form. Log base 2 of something equals log base 2 of 15, because that's my exponent, that's my argument. So when we convert, x is 15. Same idea. Ln of x equals ln of 5. Well, x equals 5. Ln of x equals, because if we have an x there, that's our unknown. Ln of x equals ln of 3. E squared times the ln of 5. Well, that one's a little bit trickier. There's now, so if I do ln of x equals, that should be 10, I think. This one is buzz off. 2 ln 5 equals what? Oh, 5. 5 ln times 2 equals e to 25. What am I missing here? Because well, there's one property that can put that up there. The 2 can become an exponent, and then those cancel, and that would be 25. Because that's not making any sense. I must have messed something up. Where am I going? I may have to return tomorrow with a better explanation of those ones. What do we have left? I think just a page and a blank. Unless there's something hiding down there. Go away. That doesn't. Yeah, I'm gonna have to come back to you as to why that does equal 25, but an explanation for that would be a good thing. But it's Monday morning and I'm having a bit of a brain fart. E is the base of growth shared by anything that's growing continuously. We talk about compound interest in the sense that we can use 1 plus the interest rate to the power of something. But technically, we can also write that as a function of base E. It's a continuous growth. It's growing the same way. Y is the amount of continuous growth over a certain period, because over a time, it's how much it's growing. The logarithm is how long it takes to get to a particular thing. And you can use these to model just about any situation. But that's other than my part on that, because we haven't done some log properties or the rules of logarithms, because that comes up later this week as to why that's 15. So we're going to have to start that and come back to it. But that's all I wanted to do today, because we're off tomorrow because it's Wednesday, and we'll be back on Thursday, if that sounds all right. Wow, we've got all sorts of people today. If you haven't heard, apparently the last day of online learning which is somewhat contradictory. Um, is that 12th? But it's the last day to have something submitted, so I don't know what's going to happen. I'm sure there's going to be more clarification and all of that. But that's all I have to do for us today. You can check the practice stuff, and I'll upload this and the video for anyone who is not here, but you guys are all here, so that should be okay. And then we'll carry on with a little bit more with graphing logarithms and properties of logs on Thursday. Sound good?
Thank you.
You're welcome.
Thank you.
You're welcome. Bye. Enjoy the sun.